It is my privilege to introduce Dr. Sudakar Chandran, who is currently working as an associate professor in the Department of Physics, IIT Madras. He did his PhD from IIT Bangalore. He worked as a postdoctoral research associate in the Department of Physics and Astronomy, Wayne State University, USA. He received DRD fellowship and worked in Aachen University and Ernst Ruska Center at Research Center. He worked as a visiting guest researcher in the Department of Material Science, Royal Institute of Technology, Sweden. Before joining IIT Madras, he worked as a research assistant professor in Department of Physics and Astronomy, Wayne State University, USA. His current research focus on microscopic and spectroscopic investigations of defects, nanostructured oxide materials for lithium-ion battery, nano oxides, semiconductor thin films, and quantum dots for solar cell applications. Defect controlled structure, property correlations in multifunctional oxides and multiferrics. In situ electrical and optical probes under high vacuum and controlled atmosphere annealing to study oxygen vacancy influence changes in the properties of oxide thin films. He has 5 patents and published 119 articles in various reputed journals, international journals. He presented his work in 47 international conferences. He awarded 5 PhD and 4 PDFs. He has executed 9 sponsored projects so far. With this brief introduction, now I request the speaker to deliver his talk on influence of disorder on the functional properties of two-dimensional molybdenum sulfide nanosheets. The duration of the talk is 1 hour, followed by 30 minutes discussion. Now I request the speaker to take over the session. Sir.
Thank you. So, am I audible now to everyone?
Yes, sir.
Okay. So, good afternoon, everyone. Thanks for the nice introduction. And my name is Sudakar Chandran. I'm from the Department of Physics, IIT Madras. So, in today's talk, I will present the influence of disorder on the functional properties of 2D MOS2 nanosheet. Okay, so I will give a brief introduction to 2D materials, and then specifically I will talk about the moly disulfide, how the defects present in the moly disulfide can be used to tailor the functional properties for some certain applications. Oops, I'm not able to move the slide. Oh, yeah. Okay, so the 2D materials, it came sometime in the beginning of 2000, it started grabbing the attention. Since then, most of the electronics, if you look at, they are all silicon based. They are bulk. Of course, the scalability was an issue. You cannot go down below a certain size. So nowadays, the focus is on sub 10 nanometer or sub 7 nanometer devices. Till 14 nanometer devices are being used in applications. But for various reasons, including the dielectric constant and so on, it could not be used. But so people started looking for other materials like that should also be thin, and it could be flexible, and so various aspects they looked at, and then the 2D materials were seen to be the promising candidate. So around 2004, Nobel Prize was given to Andre Geim and Kostya Novoselov. Okay, so they showed that 2D van der Waals material, like the graphene, one single layer of graphene can be exfoliated from the graphite. So a single layer of graphene is shown. It's like a honeycomb lattice. It's just 1 atom thick. And generally the graphite has multiple layers of this. If you can remove just 1 layer and place it on some substrate, and it exhibits very exotic properties. It becomes transparent, its conductivity, high thermal conductivity, and also its strength is very different than when it is in the bulk form. So all these advantages has led to exploring the 2D materials extensively. Okay, so of course the 2D materials from the science or knowledge point of view is not nothing new. It was known in the early 1930s, Landau and Pierce, they showed that they suggested that 2D crystals could not exist. But then later the band structure of single layer graphite was calculated, and then the graphene name itself was given by Hans Peter Bohm, and a lot of the theoretical studies followed, giving a lot of useful informations and interesting properties these single layer graphite material can give. So for example, graphene can, by theoretical studies, it was shown that massless Dirac equation and anomalous effect in graphene. So the moment they extracted single layer of graphene and started studying a lot of interesting properties, it became boom. Like 2D materials became very attractive. And in fact, Andre Geim and Novoselov, they exfoliated other crystals 2D from from the layered structures like boron nitride and several other transition metal dichalcogenides and so on. So 2D materials, they are called van der Waals material because the layers are held together by van der Waals forces. So they can be broadly classified into three kinds. First one is called unary compounds, and the binary and ternary. Unary are basically the layers made up of a single material. So they are mono elementary materials. They always end with E and E, like graphene, ene, right? So it basically means single. So generally these kind of materials are classified as exenes. So silicene, phosphorine, boroine are all the examples. So this table in the periodic table, it shows what are all the single layer exenes are known. The shaded ones are all the ones known. Binary elements include two atoms. So for example, X could be like sulfur, selenium, and tellurium. So most of the sulfides, selenides, and tellurides with some transition metals combination provide a binary 2D layers, van der Waals layers. Ternary includes three layers, like most recently well-known materials are the perovskite-based halides. Also, there are chalcogenides, which could be ternary. So any three elements involved, it is called ternary compounds. Okay, so here is one example, very periodic table. What are all the possible binary van der Waals layers? It's simply shown, and the composition generally goes like MX, MX2, M2X3, and so on. Moly disulfide is one example, and there are other examples given here. You can have a combination. The color combinations given here basically shows what metal goes with what X. So there are certain hydrides, nitrides, and sulfides, selenides, fluorides, all possible. One can get the binary compound. Okay, so so the electronic properties themselves are very interesting in these transition metal dichalcogenides, for example. If you take M and X, the combination of transition metal with chalcogen elements, it can exhibit semiconducting, or it can have a narrow band metal or semi-metal characteristics. They are superconducting. So, but different materials behave differently. Charge density wave quantum materials are known. And then there are materials which exhibit very small gap semiconductors. There are materials superconducting like palladium, telluride. So various wide range of properties are possible. One interesting thing, if you would note, is most of these materials are diamagnetic, or either paramagnetic or antiferromagnetic. There is no material which is ferromagnetic or ferrimagnetic in nature. So one of the things people started looking at is how to make these 2D materials ferromagnetic or ferrimagnetic, like basically to establish the long-range magnetic order parameter in the 2D layers. So that is what the topic I'm going to discuss today. Just 1 minute. Okay, eraser is not possible. So some line is there, so that's fine. So, the transition metal dichalcogenides have a general formula MX2. Okay, so the metal atom layer, for example, the one shown here in the blue color, is sandwiched between the X is a selenide, for example, sulfur or selenide, MOS2 or MOSE2. So the metal layer is sandwiched between these sulfur or selenide layers. So it gets stacked up. So this is one monolayer, and so 2 layers are shown here. And the metal to metal bond lengths are typically in the range of 3.15 to 4.4 angstrom. The sheet thickness is roughly about 6 to 7 angstrom. The distance between the sheets is also around that same distance. So the moly disulfide or transition metal dichalcogenides, they exist in various structural forms. 1T, 1T prime, 2H, and 3R are the different phases known. For example, they differ in the way the moly and sulfur layers are arranged. For example, if you take 1T phase, the top sulfur layer is A, and in between moly is B, and the bottommost sulfur is C. So it's like ABC stacking. As you might have studied in the cubic close packing stacks, ABC stacking is what the 1T phase has. Whereas the 2H phase has a ABA, BAB stacking. So this repeats afterwards. And there is also another phase which is called 3R. It has a ABA, BCB, CAC, and then it repeats. So they differ in the way the layers are stacked. There is also another phase which is called 1T prime. The 1T phase itself is not stable at room temperature. The 1T prime it has a distorted octahedral geometry. Generally, in these 2H and 3R, the moly occupies the trigonal prismatic side, the coordination side. Whereas in 1T, the moly sits in the octahedral side. Okay, so when the phase transition from trigonal prismatic to octahedral happens, there is a reorientation of the sulfur atoms, and therefore this particular trigonal prismatic can get down to the octahedral phase. That happens at high temperatures. Okay, so okay, so of course, depending on the moly, where exactly in what coordination it sits, you will have a crystal field effect. For example, if it is in 1T phase, it's a 4D2 system. Therefore, you will have 2 unpaired electrons. Whereas in its trigonal prismatic configuration, the crystal field is such that you have a low spin configuration. Therefore, these 2 spins will get paired up, and therefore it exhibits a diamagnetic characteristics. So 1T phase can be made into ferromagnetic state. So there is a lot of interest to how to alter the 2H to 1T phase in a stable manner at room temperature. So that is the kind of study a lot of people have taken up. And for example, the different phase transitions that are known in the transition metal dichalcogenides are listed here. And you can convert the hexagonal 2H phase to octahedral 1T phase, or the 2H and 3R can easily, many a times when you grow the crystals, 2H and 3R are the ones that coexist together, and it's also very difficult to differentiate them. The 1T phase can get to a distorted octahedral form. And of course, at very high pressures, one can get it onto the orthorhombic structure. And each of these different phases have interesting properties. As you can see, the hexagonal phase exhibits the direct, indirect band gap transition, metal insulator transition. And these 2H phases are one-dimensional, two-dimensional charge, density wave, quantum materials. It can exhibit superconductivity and so on. So each one of these different phases has its own interesting properties, and most of the studies are aimed at exploring these properties. Okay. So to comment on how these transition metal dichalcogenate layers, nanosheets are prepared, one of the simple method is mechanical exfoliation. You can get the crystalline quality for electrical property studies. So what you need to do is take a adhesive tape and put it onto the bulk crystal and strip it off. So a couple of layers will stick onto it, and you can repeat this process in such a way that finally you will have a single layer sticking onto the tape, and that you can carefully transfer onto the silicon dioxide substrate. And finally you have these monolayer crystals onto the and then you can put the probes and study. But the disadvantage of this technique is you don't get anything beyond a few tens of micron, maybe 100 micron, nothing beyond that. So if you want for applications, you should be able to grow them in a large area. So CVD process is one of the process in which you can grow a large area crystals. Of course, a lot of process optimization is required. That itself is a deep research that is going on. The other way of doing it is you take the bulk material, intercalate certain alkali metals like lithium, and when these lithium they get into the interlayers, they can by dissolving and then sonicating it, you can separate all these crystals, and then you can have it in the dispersed solution, or you can transfer it onto the substrate. So these are all the ways. There are many other physical vapor deposition and chemical vapor depositions are being explored to grow large area single layer crystals. So these in these transition metal dichalcogenates, for example, invariably you get defects. The defects could be of various kind, okay, and it can alter the properties of the material. Therefore, it is very important to know what are all these defects and how it can influence the properties. So the prominent defects are point defects, dislocations, and dopants. For example, if you see this, these are all zero-dimensional, means they are all point defects. You have a missing moly or sulfur atom, or some other element can sit at these sites as either as an add atom or a dopant atom or substitution atom. That is the zero-dimensional defects. The one-dimensional defects are the grain boundaries or the edges. So they all form a one-dimensional, or if you have a heterostructure, the boundary between these two layers form one-dimensional defects. And if you have a hetero layer stacking of two different material, then that forms kind of a 2D defect. Also, 2D defect can arise from the folding, wrinkling, the way the sheets get scrolled, and also the sheets are never flat, and there will be a lot of rippling. So these all give rise to the 2D kind of defects. In fact, these kind of defects can be introduced into the system either by doping or by bombarding the sheet with high energy electron or proton beams or oxygen plasma irradiation and so on. So a lot of systematic studies are being explored to study how these defects can alter the optical, magnetic, and other functional properties. Okay, so now with that introduction, I will get on and show how one can tailor the magnetic properties by activating defect sites in MOS2 nanosheets, magnetically activating the sites in MOS2. Remember, MOS2 is a diamagnetic because of the trigonal biprismatic coordination, where the crystal field is such that, you know, the lowest energy level occupies two unpaired electrons, and they pair up, therefore net magnetic moment is 0. So in this study, what we did, we prepared a moly disulfide using a chemical method. The procedure is typically shown here. This is a well-known procedure. So at the end of these procedure, you get brown precipitate, which you annihilate at 500 degrees Celsius. You will get sheets. Typically, the sheets are around 200 to 500 nanometer in the area wise. So they are very very small. Of course, you can anneal at different temperatures under inert or slightly reducing ambient, so that it doesn't get oxidized. So under these conditions, you will see, you can alter the defect structure in these. So the defect, for example, as it is shown here, the 500 annealed one is very broad, which means, you know, the crystallite thickness is very, very small. And then as you increase the temperature, it becomes very sharp. So the thickness increases. Also, the defects in the nano sheets gets altered. Raman spectroscopy also can be used to show how the defects in these MOS to nanosheet change. This particular one shown in the box here is a defect mode, defect activated mode. And as you anneal it, this intensity goes down, and that can be used as a quantification for the presence of defects. Of course, you can see with annealing, the distance between the layers change, or the lattice parameter changes. It decreases, whereas the lattice parameter A increases. So the annealing effect, where the defects are controlled, has an influence on the lattice parameter. And this is the particular way you can analyze the Raman spectra to infer how the intensity ratios of the normal vibration modes changes with the defect modes. Okay, so to give a little good insight on what are these defects and how do you see there are defects, here I have put a collage where moly prepared at 500 degrees Celsius, 700 and 900 are shown. As you can see, there are a lot of wrinkles. Just look at this low mag image. Very immediately you can find out the crystals in the 900 are kind of flat, straight, whereas here in the 500, a lot of wrinkles are there. They are much smaller, and that is kind of in between in the 700 degrees Celsius anneal sample. So pretty much you can get convinced easily by careful annealing and number of hours you anneal at a given temperature, you can get rid of these defects. And we have estimated the concentration of these defects by counting the edge termination, dislocation, other folding and bending defects. You can see that the defects are very high when it is low temperature anneal, whereas high temperature anneal ones, they have almost 10 times a smaller defect. Okay, so to show what these defects within the plane look like, so here is the high resolution image taken from one of the sheets. Of course, these sheets are not monolayer; they are multi-layers. For example, you can see the number of layers here. How does it change? Typically, it is 6 to 7 layers for 500 degree anneal sample. Of course, it increases as you increase the temperature. So obviously, you cannot keep by the process we used, we cannot keep the thickness same and then alter the defect. That's one of the disadvantage. In spite of that, what you can strikingly see is if you take the high resolution image and then also calculate the lattice fringe strain involved in the lattice fringe, the 500 degree has a lot of strain. The strain mapping derived from these fast Fourier transform, the filtered images, shows that 500 degrees Celsius annealed sample has a large strains, whereas the strain is pretty much not there much in the 900 degree annealed sample. So, of course, our interest was to study what happens to the magnetic properties. In these compounds, the moly exists both in 4+ and 5+ oxidation state. The 5+ comes because of the defects present in the edges, point defects, and so on. And 500 degrees Celsius has a large concentration of these defects. So whenever you have these kind of defects, what would happen is that there could be trapped charge carriers. And since moly can have an unpaired electron in the 5+ state, single unpaired electron in the 5+ plate because it's oxidized state, right? So then the single spin associated with it can interact with these defect sites with the trapped charges, and that forms the magnetic polar ions. When you have sufficient concentration of the moly 5+ and then the defects, there could be overlap of the magnetic polar ions, and you may get the magnetic properties enabled. And that's what we found here. So here we have shown with defects, that means 500 to 900, how the magnetic properties change. You can see that 500 annealed samples exhibit high magnetization. As you increase, they become low. In fact, they become diamagnetic in nature. In the temperature-dependent studies also, you can see the ferromagnetic-like transition seen around 120 Kelvin. And we believe this, the ferromagnetic nature is because of the dilute magnetic-like situation in these nanosheets. In fact, we wanted to explore, this is only pure MOS2, no magnetic dopants were there. Therefore, we wanted to see can we tune the magnetic properties by controlling other ways, the defects, like transition metal doping. And also, as I mentioned in the beginning, if you use the structural phase transition, the 2H to 1T phase, can it be done? So let me give the first transition metal doping, what we found. So we took cobalt and manganese as a case study, and we doped from 0%, which is the pure MOS2, to all the way to 25% in both the cases. Manganese, it doesn't show much variation either in the XRD or Raman studies, whereas in cobalt doped one, certainly at very high concentrations, you happen to see the secondary phases like CO9 site segregating. Doping also influences the layer thickness, the number of layers you have in the nanosheets, and the crystallite size and so on. So in spite of that, of course, what we see is the doping is very uniform. When we did the EDS mapping on the shades, they seem to be uniform. And of course, there is no specific any segregation of these we found, except in the high concentration, more than 10%, you happen to see the XR device, you see the CO9 site phase, which is in fact magnetic in nature. So below that, obviously what you see is as you increase the doping concentration, the magnetization increases and comes down. In fact, increase in the magnetization for the cobalt doping is almost 10 times more than manganese doping. You can appreciate this change from the saturation magnetization shown at both 5 Kelvin and 300 Kelvin in these plots. So initially there is an increase, and then it starts increasing, and again it increases. But the change is only here from close to 0 to 0.02 EME per gram. Whereas in the case of cobalt doping, it's much higher. For example, this is 0.05, whereas here 0.8 up to 0.8. So almost like 10 times increase the same. You can also measure the Bohr magneton per dopant atom, which shows a gradual decrease. So which means, this is the typical nature you will find in dilute magnetic semiconducting system. So this particular system behaves just like dilute magnetic semiconductors. So this study showed as, cobalt doping seems to be promising. Of course, there is always a question of whether the cobalt segregation is happening, which is contributing for magnetic study. That is always there. But this particular behavior, initially the magnetization increases and then decreases, basically tells initially you have a dilute magnetic semiconducting nature dominating, and it decreases because the antiferromagnetism takes over. Therefore, in this region, you have both antiferromagnetic and DMS state. But beyond 10%, the cobalt sulfide phases segregate, and therefore you see this increase in the magnetization. So doping is always a tricky, so one has to work at the right doping concentration. Here in this slide, I will show the other way of another way of manipulating the magnetic property in the moly disulfide nanosheets. So what we did, we took these moly disulfide, the same moly disulfide as I discussed in the previous slides, and we took it as one of the electrode, and then put it as a lithium half cell with the lithium metal as an anode, and then did the intercalation. So to start with, you have these moly disulfide separated with layer. The layer is, nothing is there in between the layer. When you intercalate, these lithium ions get in between these layers. And that's when the 2H phase converts to 1T phase. Okay, and of course, once it gets converted to 1T phase, it doesn't go back to 2H phase. It remains in 1T prime phase, where the octahedra is distorted. So here you have a distorted octahedra. In this case, you have an octahedral geometry. And using this, we wanted to see how the magnetic properties get altered. So, of course, here we show how much lithium can get into the moly disulfide. For example, when you have a defect-rich moly disulfide nanosheets, you can see typically 1 lithium is what it can go. For example, sorry, where did I go? Yeah, so the X is 1. LiMOS2. Of course, if you try to push too many lithium, the moly disulfide is not stable. Li2S will come out and moly will get thrown out. So it becomes a two-phase scenario. From that onwards, it's kind of a lithium sulfide battery. So Li and Li2S is the reactive agent. So we control the voltage such that we don't go below 1 volt, in which case only maximum of 1 lithium is all possible. But even in that range, in the bulk samples, even in that range, what we found, if you have a defect-rich nanosheets, this particular electrode takes up 2 lithium. In 900, we found it takes up close to 1.6 lithium. So excess lithium is taken into the system because of large edge defects and other defects present, the folding and other defects present in the system. So these lithium can go and get decorated on these defect sites, and therefore it would alter the properties. So of course, we did a detailed study on using the XPS, what happens to the oxidation state and so on. Mostly we see 4+ oxidation state in the pristine form, whereas the lithium is taken, it gets onto the 3+ state, and that's what this equation suggests, right? So if you put 1 lithium and the moly in this is in 3+ state, that's what we found. Of course, in some cases you see moly in metal state also because of the reduction we have done. In any case, if you look at the magnetic properties, the pristine one is a black here, very small, right? And then the moment you do the lithiation, the blue triangle here. So it jumps from here to this much. So there is a big jump in the ferromagnetic nature that you can also see when the measurements are done at room temperature. When you reversibly extract the lithium, right, then it comes down. The magnetization comes down. So the reversible extraction, as you can see here, initially we could put 2 lithium in Li in MOS2, but when we reversibly take it out, we could get approximately 1 lithium only in both the cases. So the large amount of lithium is retained in defect-rich nanosheet, whereas the retained lithium is less in this case. So in moly disulfide, which is kind of a defect suppressed, the lithium, when it is extracted, it doesn't change much, as you can see. So there is a lot of interesting thing which is happening, and that can be understood from this particular picture. So you have a defect-rich moly disulfide to begin with, in which both the 4+ and 5+ moly is in 4+ and 5+ state. The moly in the defect sites are mostly in the 5+ state, which will have an unpaired electron. And this unpaired electron is what explains the magnetic properties of the pristine MOS2 in the defect-rich case, like the bound magnetic polaron model I explained. Now, when you put lithium into this, 2 lithium is taken, and these lithium go in between these layers, and also they go on to the defect sites, and then they get trapped, adsorbed, or trapped. So you have a moly 4+ going to moly 3+, also these moly 5+ gets to moly 4+, and this will have now, if the trigonal prismatic configuration is, I think mostly it is, when it is a defect side, it doesn't go to the octahedral geometry, and trigonal by prismatic, in that geometry, you have a diamagnetic state. So it kind of, you had a magnetic property coming, which kind of disappears, whereas the magnetic property, the diamagnetic state of moly 4+ becomes magnetic now. Of course, this is a large concentration. Therefore, you see a big jump in the magnetic property here. So from almost 0.0 something to 0.4. Okay, so when you try to get the lithium out, roughly about 1.3 lithium comes out. The rest of it is still there. And in this state now, moly goes to this moly in the octahedral geometry. It cannot go back to trigonal prismatic geometry. It will be in the octahedral geometry, but then it gets distorted. And therefore, you will have 2 unpaired electrons. So therefore, the magnetization goes down. Okay, so, and that's the same thing, but except that, moly disulfide defects suppressed, initial increase is less, but then the change is much larger than here because of the moly, the octahedral contribution, the unpaired electrons, number of unpaired electrons that comes from the octahedral geometry. Okay, so that is an interesting thing we found. So this particular picture kind of explains how the magnitude of the magnetization value we find in moly disulfide, how it would change. So this is the pristine case where the magnetism mainly arises from the moly 5+ defects, defect sites in association with the sulfur defects that would exist. So these form the polarons, overlapping polarons have all the spins oriented. Whereas in the lithiated case, the moly themselves, they become 3 unpaired electrons they contribute. So S is equal to 3/2 from the moly 3+ state. And therefore the defect states present, they also pull all these, the interaction, and therefore they make it ferromagnetic. So therefore a large increase in the magnetization is seen in this state. When you go back to the delithiation state, the moly 4+, this still has a 2 unpaired electron. Therefore there's a slight reduction, but then still you will see that the ferromagnetic state is retained. So So this is one of the interesting study we found. Of course, you might see in the literature many such studies which try to understand the ferromagnetism. The recent one, some 2 years back. So the one interesting one we found is what they have done is they have grown these moly-disulfide triangular features, but then it is not monolayer. It is grown in such a way that it exhibits pyramids. So big sheet of layer, and then you have a lot of sheets stacked on top of it. So it forms a pyramidal structure. So in this case, the edges, each pyramid, as the size keeps on decreasing, you have a lot of edges, right? So these edges, they call zigzag edges, are many in these crystals, like you can see in this particular case, lots of edges, and therefore the zigzag edges have a ferromagnetic nature. So what they showed is, by changing the zigzag edge configuration, they made the ferromagnetic nature. And that can happen even in the nanosheets, what we discussed. So you have edges that are magnetic in nature, and there are edges that are non-magnetic in nature. So there are two kinds of edges you will find: zigzag and armchair edges. The armchair edges are non-magnetic in nature, and whereas the zigzag edges are magnetic, and they give 2 MeV per moly magnetic moment. Okay, so enabling magnetic properties. Of course, in this case, the magnetism comes from the edges, but if you can get magnetism from the uniformly across the sheet, then that is where the interesting properties can be studied. Magneto-resistance, magneto-electronic or spintronic applications, you can make use of these sheets. Okay, so I think I may have another 10 minutes. So I will quickly show the moly-disulfide. What we studied can also be used for lithium-ion battery application, the same set of nanosheets, and it leads to high rate capability anode. Of course, it doesn't come with all glorious parameters that you look for, but there are certain interesting signs you can learn from these studies. So moly, of course, lithium-ion batteries is nowadays, it's full-fledged. Everyone want to get the electric vehicle up, and a lot of research is going on to find out the appropriate materials which has a high specific energy and high specific power. In addition to that, you want the charging discharging to happen at very high C rate. Generally, if you have a battery, if you try to extract the charges quick, the specific energy that you can get at high C rate goes down. So that's one of the challenge. So people are trying to address how to get quick charging and quick charging, especially, and quick discharging without losing the stored charge. So the other problem is, the graphite, which is most commonly used anode, has something around 370 milliampere hour per gram of specific charge. And now people are looking for materials that can give much higher specific capacity. For example, silicon was one of the promising composition, but then the problem with the silicon, it has a very high volume expansion, and therefore in the electrode it crumbles into powder, and it doesn't work for large cycles. It might work for a few cycles, a few tens. After that, it's gone. So moly disulfide is a promising candidate in that sense. So we explored the properties in moly disulfide. In fact, gives all these tunability, microstructurally you can tailor, size you can tailor. You can also coat it with certain carbon material. So this is what I showed. So we took the same 3 samples, and then I will show to convince you how the defect. See, these are all the bending defects, and then the curling defects. The edge defects are shown. Some of the edge defects are shown. So in these regions, always the the sheets terminate. Therefore, you have the one-dimensional defects that I mentioned. So all these kind of defects are there, and the concentration of this can be just tailored by annealing at different temperature, different hours and temperature. So in this one particular study, we took 800 1 hour, 800 5 hour, and 900 1 hour MOS2. As you can see, 900 already the crystals are straight. So at least you don't have the bending, folding defects in large, but there are other defects still prevailing. So this influences the electrochemical property. Okay, so this I already mentioned, so let me skip this. So in what way it does is, if you do the cyclic capacity, so these measurements are done, some of these measurements, as you can see at high C rate, 25 C, 30 C. So it can work at very high C rate, still giving high specific capacity. Of course, these measurements are done up to 1 volt, where the 1T phase is there. If you go below 1 volt, the Li2S moly will segregate out. Okay, so we wanted to keep in the moly sulfide MOS2 form itself and then study. That's why the capacity is a little less. But then what we found is the cyclability is much better as if you have the defects. Okay, so that's one of the things we found. In addition, the high C rate, you get the cyclability, and the reason the cyclability and high C rate can happen is these lithium go on to the defect sites, and the migration of the lithium is facilitated by the lithiums that are trapped at these defect sites. Okay, so so the excess lithium which are present in the defect sites on the edges, they kind of facilitate the improvement in the electrochemical properties. In fact, we also studied the extreme cases like 500 and 900, as I discussed in the magnetic properties. One interesting thing we found is when you do the cyclic studies at high C rate, you see that the 500 one, initially it keeps on increasing, almost up to 500 cycles, it shows an increase in the capacity. Almost it goes from 0.2 to 0.3. And then it slowly decreases. Whereas the 900 one, it keeps on decreasing. So the structural changes that happen with the cycling means, the lithium is intercalated into the system and then removed from the system, and this is being continued, and every time checking how many lithium is going in and how many lithium is coming out. So we see that whenever you have defects, initially the intakes keeps on increasing. So the defect is doing something to the structure, it makes it to take more and more lithium to begin with. Whereas in the highly crystalline defect suppressed nanosheet, it doesn't allow the lithium to take. Of course, you do have very less lithium in the first place taken into the system in the defect-rich nanosheets. This tells, after certain 500 cycles, both the system converge to more or less similar structural feature. So this is something one should explore. So that's where we are looking at what are all the structural changes are happening and so on. So just to summarize this, the excess lithium trapped at the defect sites, they play an important role in deciding the cyclic stability in MOS2 electrodes. Yeah, so therefore, it enables a high rate capability in the material. So this particular Ragun plot, it shows, if you have defect rich, the specific energy is higher. You can also have the specific power higher. Defect suppressed ones always have little compromised values. Okay, so with that, let me summarize a few other works. So kind of a review, just a couple of works. I will show where the defects can play the role. Here is one example which shows the moly disulfide in moly disulfide single layers. The photoluminescence can be enhanced if you introduce oxygen defects. So in this particular work, what they did, they had a lot of cracks and defect sites, and from that place they see the emission being very high, and they suggested that the recombination is minimum non-radiative recombination of excitons from the defect sites as minimum. Therefore, it enhances the PL emission properties, and also the chemical absorption of the oxygen induces p-type doping, and therefore this kind of materials are interesting for photoluminescent applications. So in another study, it is also important that the molybdisulfide is used in water splitting and other applications. So the defects are shown to have a strong influence on the water splitting capability. So the excess sulfur, whenever you have it, it is shown to promote the screw dislocations, and especially in CVD grown samples, they have shown this. And therefore, it influences the hydrogen evolution reaction in the electrochemical cell. So very interesting study. So how defect can be used to tailor the properties. And also people have shown, for example, the sulfur, when you grow them in the CVD method or some other method, so the sulfur evaporation, how it can enhance the screw dislocation. So these are all the like pyramid-like structures, what I discussed earlier, something of similar thing. So it increases such dislocation. So there is a way to control the defect concentration in this. So molybdisulfide is very promising, and I must show this one slide where people from the researchers from the Lawrence Berkeley National Laboratory have already successfully built a 1 nanometer long transistor gate, which is the smallest device. So this uses carbon nanotube and also molybdisulfide kind of a transistor. So that's the smallest device people have shown. So molybdisulfide is very promising in that sense. So 2D materials are very promising, though I discussed molybdisulfide because I'm working on that, and therefore I'm more familiar with it. There are many other two-dimensional materials with exotic properties, and these properties needs to be explored. Therefore, the properties can be tailored, and the studies in the device form is yet to be realized. Of course, we have a long way to go in understanding the science of these 2D materials. So with that, let me stop the presentation. If there are questions, I will take up.
So it is time for discussion. You can type the questions on the chat box also.
I should go to the chat box and see, or?
Yeah, so far they are not given any question. The session is open for discussion. You can unmute and ask the question.
No questions?
Yeah, I request the participants to raise your hand and unmute yourself and ask the question, or you can type it also.
What is the origin of magnetism in this MOS2?
As I said, if we go back to that, maybe this particular slide will explain. So dilute magnetic semiconductors, are you familiar with? So in oxide systems, when you have a transition metal dopants, then the magnetic interaction through the magnetic polarons, that gives rise to a long range order. So for example, here you have these paramagnetic sites, right? They are scattered. So generally, if you have a defects, they'll be paramagnetic in nature. Whereas when you have certain defects like sulfur vacancies, they always have a trapped charges, and these trapped charges from the sulfur vacancies, along with the unpaired domains, they interact and form kind of magnetic polarons. Of course, these magnetic polarons can be segregated, but if you have a large concentration of these paramagnetic sites as well as the defects, then there could be overlap of these, like the one shown here. These two overlap. Of course, if you have something else, it can overlap and it can permeate. So when such overlap happens, within the magnetic polaron, all the spins will be oriented because of the interaction, the strong interaction. Okay, so when they overlap, the interaction is now kind of permeated, and then the spins are all oriented in the same direction. In the other regions, it is not. So when you have sufficient concentration of defect sites and also spins, you have a long range interaction, and therefore the ferromagnetism is seen. Like in this case, you have moly in a 3+ state, which gives rise to 3 unpaired electron when it is present in the octahedral site. So if it is not a part of this magnetic polaron, they're all just like paramagnetic sites. But if they are overlapping, they're all oriented in the same direction, as schematically shown. All the spins within the circles, they are oriented in the same direction. So the overlapping magnetic polarons will have spins oriented in the same direction. And if this is permeating because of the concentration of the defects, then you will have long range order. And that's when you happen to see the magnetic ferromagnetic like behavior.
Okay.
There is
also what is the typical Curie temperature of these samples?
Yeah, so for example, what we found is like 120 Kelvin, but there are people who have also showed a very high temperature for this, and of course not experimentally it has been found, but they extrapolate the temperature dependent magnetization curves and then try to find the Curie temperature. And I think I forgot the number, but it's a high temperature also has been proposed for this. But then the system, what people have studied is slightly different, where they have a MOS2 phase, something like this. They don't have this situation where sulfur defects and paramagnetic moly are there because of the defect nature. What they have is locally, they have a 1T phase. Means in MOS2 you have a trigonal bipyramid